Welcome to The Explainer. Today, we're diving into a really wild idea from the Principia Cybernetica project. It tries to solve two of physics' biggest, most stubborn mysteries with a single, radical answer. And honestly, it might just change how you see everything.
So let's just get right to it. Here is the core question, the big idea that this whole thing is built on. What if we've been hunting for dark matter all wrong? Searching for some exotic, invisible particle, when the answer is actually the gravitational footprint of life itself. Yeah, it's a big swing, and it forces us to completely rethink the link between life, information, and the cosmos.
Every good detective story needs a crime scene, right? Well, in physics, our crime scene has two major unsolved cases. These are two persistent, nagging glitches in how we understand the universe, and they have had physicists scratching their heads for decades.
And what's so weird is that these two clues couldn't be more different. On one hand, you've got the Flyby Anomaly. This is happening right here in our solar system, where spacecraft get these tiny, unexplained speed boosts. On the other hand, you have the GZK paradox, particles with truly impossible energies arriving from the depths of space. They're from totally separate fields of physics, and yet nobody has a standard explanation for either of them. For years, the investigation into both of these was pretty much stalled. But this new framework points the finger at a suspect that, well, nobody saw coming. It asks a really strange question. What if information isn't just bits and bytes? What if it has a real physical presence? What if information itself has weight? Okay, so this is the absolute heart of the idea. It's called M-theta coherence. Let's break that down. The theory says that gravity doesn't just respond to matter and energy, the stuff we can see. It also responds to highly organized, complex information. Think about a biosphere, a system constantly using information, copying it, processing it. The idea is that this sheer density of information creates its own kind of mass, a gravitational shadow that we've been misinterpreting as dark matter.
All right, let's take this radical idea and apply it to our first case file, the Flyby Anomaly. Because if this is right, that weird nudge our spacecraft feel isn't some error in our calculations. No, it's the first time we've ever directly detected the gravity of life itself.
And this right here is the smoking gun. The theory makes a really clear prediction. You should only see this effect around a planet with a super dense, complex biosphere. And guess what? The data we have lines up perfectly. We see the anomaly at Earth, the one planet we know is teeming with life, but when spacecraft flew past Mars or Venus, geologically active but as far as we know lifeless, the effect was gone. Nothing, not a trace. So you have to ask, what is generating this effect? Well, it's the mind-boggling amount of information processing that life does. I mean, think about it for a second. Every single cell dividing, every neuron firing, every leaf turning sunlight into energy. The entire biosphere is like one giant planet-sized computer, processing an estimated 10 to the 38th bits of information every single second. The theory says that that is what's creating this extra gravitational pull. Now here's the crucial part. This information field around Earth isn't some gentle, fuzzy cloud. The paper calls it a biospheric cliff. Imagine you're flying through the near-total informational emptiness of space, and then, bam, you hit the thin shell of Earth's biosphere. The jump in information density is almost instantaneous. It's a sharp vertical edge in space-time.
Okay, so how does a cliff create a force? The proposed mechanism is really cool. It's called geometric jerk. The idea is that the kick the spacecraft feels doesn't come from the static weight of the biosphere. That would be way too small to measure. Now, the force comes from the incredibly rapid change a spacecraft feels as it blasts across that boundary. It's like driving your car. Cruising on a smooth highway is fine, but if you hit a massive pothole, that sudden change gives you a jolt. It's not about being near life, it's about crossing its edge at incredible speed.
And this neatly explains why the anomaly is so specific. Think about a satellite in a nice, stable orbit. It's just flying along the cliff, parallel to it, so it feels nothing. But a spacecraft on a flyby, it's on a completely different path. It's literally punching through that informational wall at tens of thousands of miles per hour. That little kick it gets, that's the impulse. It's the sonic boom of hitting that information shell. Now, of course, people have tried to explain this before. Back in 2008, a formula correctly figured out that the key was the spacecraft's geometry, its specific angle in and angle out. But that formula had a big problem. It assumed Earth's field was perfectly symmetrical, perfectly smooth.
So when the Juno spacecraft flew by in 2013, the formula predicted it should have seen a big effect. But the actual measurement? It was almost zero. That was a huge failure for that model.
And this is where the new theory comes back in with a brilliant solution. It says the problem isn't just about geometry, it's about geography. The information field isn't smooth at all. It's lumpy. It's concentrated over the continents, over the rainforests, over the cities. So what about Juno's path? Well, it just so happened that it flew mostly over the information-poor Pacific Ocean. It missed the densest patches, which perfectly explains why it saw almost nothing.
Okay, so that's case number one. The theory seems to hold up pretty well. Now let's zoom way, way out. We're going to apply the exact same thinking to our second mystery. Out in the vastness of deep space, the puzzle of the impossible cosmic rays. So here's the paradox. We detect these cosmic rays hitting our atmosphere with so much energy that scientists literally called them oh my god particles. But according to standard physics, a particle with that much energy shouldn't be able to travel across millions of light years. It should interact with ancient light from the Big Bang and basically run out of gas. And yet, here they are. The proposed solution here is just as mind-bending. What if these particles aren't traveling from far away at all? What if they're being created locally? The theory asks us to imagine the vacuum of space not as empty, but as an elastic medium, like a rubber sheet stretched incredibly taut, storing a huge amount of tension. And you know what happens when you stretch a rubber band too far? Sometimes it snaps. The theory suggests a local patch of space-time can suddenly realign, releasing all that stored energy in a violent shockwave. And if a random straight proton happens to be in the wrong place at the wrong time, it gets caught in that wavefront and accelerated to unbelievable speeds. So the accelerator isn't a galaxy billions of light years away. It's the fabric of space-time itself, snapping, right in our own cosmic neighborhood. The paper uses this metaphor, and it's just perfect. It says these cosmic rays are the earthquakes of space-time. We're not seeing a bullet fired from a distant gun. We're feeling the local tremors from cracks forming in the medium itself. And that's why we can never find their source. The source isn't an object. It's an event in the vacuum. So let's bring it all together. This is what's so powerful about this whole framework. It's not two separate ad hoc solutions. It's one single fundamental idea, that coherent information has a physical gravitational effect that seems to solve both mysteries, one at the planetary scale and one at the cosmic scale. So the common thread is that our current physics is missing a piece of the puzzle. It's missing the gravitational effect of information, this m theta. Earth's biosphere creates a tiny local information field that nudges spacecraft. And on a huge scale, stresses in the universe's overall information field create space-time earthquakes that launch cosmic rays. Both anomalies, in this view, are just the first hints of a part of reality we never knew existed. Okay, I know, this sounds like science fiction, but a good scientific theory has to be testable. It has to make a prediction you can go out and check. And this one makes a clear, definitive prediction. And the best part, we don't need a new billion-dollar mission. We can test it with data we already have sitting in an archive. Here it is, the geographic correlation test. The idea is so simple, it's beautiful. You go back to the NASA archives, you pull the high-resolution telemetry from every past Earth flyby, and you map the spacecraft's exact trajectory over the surface of the planet. The prediction is crystal clear. If the theory is right, the tiny kicks in velocity, the gravity bumps, must line up with the moments the spacecraft crosses from the empty ocean to a dense landmass or over a major city. If that correlation is there, it's game over. And that leaves us with this final, absolutely profound thought. If this is true, if life really does cast a gravitational shadow, it could completely change how we search for life in the universe. Maybe the best tool for finding ET isn't a radio telescope listening for a message. Maybe it's a gravity detector listening for the weight of an alien biosphere.